Now we'll study about uh, the composite bars subjected to temperature stresses. Question is, a bar of brass 25 millimeter diameter. This is a bar of brass. Okay, this is a bar of brass 25 millimeter diameter enclosed in a steel tube of 50 millimeter external diameter and 25 millimeter internal diameter. The bar and the tube are both initially 1.5 meter long and are rigidly fastened at both ends using 20 millimeter diameter pins. Find the stresses in the two materials when the temperature rises from 30 degrees Celsius to 10 degrees Celsius. Modulus of elasticity of steel and brass are given, and coefficient of thermal expansion for steel and brass is also given. Find also the shear stress induced in the pins. Okay. So what are the data given? This rise in temperature is given. So we can find out we can write what is the increase in temperature. Okay. So what is the increase in temperature? Increase in temperature, you can write it as increase in temperature. We are usually representing it by the letter T. Increase in temperature, T is equal to 100 minus 30, which is equal to 70 degree Celsius. Okay. Now what is the peculiarity of a composite bar? When temperature rises, the two materials of a compound bar experience different free expansions. Okay, so what is the free expansion? What is the free expansion in steel? You can write the free expansion in steel. The equation you know, free expansion in steel is equal to alpha S into change in temperature into length of the bar. What is alpha S? Alpha S is given as 11.6 into 10 raised to minus 6. What is the change in temperature or increase in temperature? 70 degrees Celsius. What is the length of this bar? 1.5 meter, which is equal to 1.5 into 10 raised to 3 millimeter. So you will get the free expansion in steel. Now we can find out what is the free expansion in the brass, which is held inside the steel tube. So we can write free expansion in brass is equal to free expansion in brass. Now here you can see the coefficient of thermal expansion for brass is very much higher than that of steel. So we can conclude that this will have more increase in length than that of steel. What is alpha of for brass? 18.7 into 10 raised to minus 6 into change in temperature is 70, and length of the bar is same, 1.5 into 10 raised to 3. So you'll get the free expansion in brass. Okay. Now, since they are prevented from separating, the two materials, brass and steel, are prevented from separating, the two materials will have a common position, which is possible only by the development of stresses. Okay. So there will be some development of stresses in these materials due to the rise in temperature. It is known as temperature stresses. As a result of the development of this temperature, both of these materials have a common position at Cc. Okay. So here what is happening? We can refer the figure, and since the free expansion of brass is more than that of the free expansion of steel, compressive force Pb will develop in brass and tensile force Ps will develop in steel to keep them in the same position. Say let it be equal to Cc. Okay, so this brass will expand more since this value is more than steel, and the steel, as a result, since they should have a common position, there should be a compressive force PB developing in brass, and since steel will have to expand for this much more length so as both of them should maintain a common position CC, there will be a tensile force acting on this brass, as a result of which there will be a tensile stress in the steel. Okay. Now we have seen that there is a compressive force PB in brass and a tensile force PS in steel. So what is the equilibrium condition? For maintaining equilibrium sigma H equal to 0, you can write this PS, tension in steel, should be equal to the compression in brass, and let us say this is equal to P, that is PS is equal to PB, and let it be equal to P. Okay. Now from this figure it is clear that this PS tension acting on the steel is producing an elongation equal to delta S, and this PB compressive force acting on this brass is producing a decrease in length is equal to delta B. So how can you write this delta S and delta B? Now we can write delta S is equal to the decrease in length delta B is equal to PL by AE, PB into L divided by AB into EB. Okay. In this, we have taken PS is equal to PB equal to P, PL by AB into EB. So this L is same as small l. So we can write here small l. Okay. PB into L by AB into EB. Okay. So now what is the increase in length? Increase in length in steel due to the tensile force PS is equal to, we can designate it as delta S. Here it is delta S is equal to PS into L by AS into ES. So this is equal to, we have taken it as PL by AS into ES. Okay. Now from this figure it is clear that alpha B into T into L minus alpha S into T into L is equal to delta S plus delta B. That is, this much distance free expansion in brass minus free expansion in steel is equal to delta S plus delta B. Okay. So we can write delta S plus delta B is equal to alpha B into T into L minus alpha S into T into L. Okay. So we can substitute these values. What is delta S? P into L by AS into ES plus what is delta B? P into L by AB into EB is equal to alpha B into T into L, that is 1.9635 minus alpha S into T into L, which is 1.218. So from this, all these values are known. L is 1.5 into 10 raised to 3. What is L? L is 1.5 into 10 raised to 3. What is AS? AS you can find out. So here we can substitute area of steel. It is given that it's a steel tube of external diameter 50 millimeter and internal diameter 25. So we can find out area of steel bar as pi by 4 into 50 square, external diameter 50 square minus internal diameter 25 square, and area of brass rod is, brass diameter is 25 millimeter, pi by 4 into 25 square. Young's modulus of steel is given as 200 kilonewton per millimeter square, that is 200 into 10 raised to 3 Newton per millimeter square which is equal to 2 into 10 raised to 5 Newton per millimeter square. Young's modulus of brass is 1 into 10 raised to 5 Newton per millimeter square. So you will get, as you can substitute all these values in this equation, and what is the unknown? Only one unknown. That unknown is equal to P, and we can find out P substituting all these values. You will get P, the load or this load due to the temperature rise at the supports will be equal to, the reaction is 20,911.19 Newton. So this is the reaction at the supports. Okay, now we can find out the answer to the question. Stress in steel is equal to PS by AS, which is equal to P by AS. P by AS is, P you have got it as 20911.19 divided by area of steel you have got it as 1472.62, which is equal to 14.2 Newton per millimeter square. Similarly, stress in brass is PB by AB, which is equal to P by AB, which is equal to 20911.19 divided by 490.87, which is equal to 42.6 Newton per millimeter square. Now we will do the second part of the question. You have to find out what is the shear stress induced in the pins. Now from this figure it is clear that the two parts of the pin is subjected to this force P. That is, two areas is resisting the force P. So which are the two areas? You have this area which is resisting the force P, and this area is also resisting the force P. Okay. So we can write the shear stress is equal to P divided by 2 into area of the pin. Okay, so what is P? P is equal to 20911.19. Now the diameter of the pin is given as 20 millimeter. So we can substitute here 2 into pi into 20 square divided by 4. So you will get the stress, shear stress as 33.28 Newton per millimeter square. So you have represented shear stress as Q. Shear stress in the pin is equal to P by 2A. So why you have taken here 2 times area? Two areas of the pin is resisting this force P. That is why you have taken the shear stress is equal to P by 2A. Area is 2 times. What is the force? Force is the force in the bars which are same, which is equal to 20911.19 divided by 2 into area. Diameter of the pin is given as 20 millimeter. So you have taken pi into 20 square by 4, which is equal to 33.28 Newton per millimeter square. Thank you.